Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 7.7 from your textbook, which introduces us to the concept of numerical or approximate integration. In this section, we're going to, at the beginning of this video, sort of review some of the approximate integration strategies you probably covered in Calculus 1, the left endpoint and right endpoint approximations. We'll also briefly discuss what is called the midpoint approximation, which hopefully you also saw in Calculus 1, but in case you didn't, we'll go ahead and sort of review it here. And then we'll also move on to a new approximation, sort of exclusive to this class, which is called the trapezoidal approximation. So in this video, we're mostly just trying to get some basic ideas down about what approximate integration is, what are some of the strategies for doing it. Then in sort of follow-up videos to this one, we'll go ahead and actually understand how accurate these approximations are and how we can actually measure and understand the error that's intrinsic when you're trying to do approximate integration. So, what is approximate integration? Well, approximate integration attempts to estimate the area under a curve, or if you prefer, it attempts to estimate a definite integral, using simpler shapes that we can easily find the area of. And at least at the beginning, we're going to be mostly focusing on using rectangles, but later on we'll use slightly more complicated shapes, but the main point is to always make sure that we have a shape that we can easily find the area of. To start off with, let's go ahead and review these sort of approximations that hopefully you saw from Calculus 1, left endpoint, right endpoint, and midpoint approximations. So to do that, let's consider this sort of diagram. So let's give ourselves something that we're interested in sort of working on. So let's imagine that we have some axes, and maybe we have a function f of x that looks like that. So there's our f of x, and maybe we're interested on some interval from a to b here. So we're working sort of from A to B. The main idea for any sort of approximation is that the first thing you're going to do is you're going to sort of divide up this interval into some pieces. So we're going to go ahead and divide this up into some equal pieces here. So maybe we end up doing something like that. And then we usually sort of label these, right? We actually call the beginning of our interval x0, then this would be x1, x2, so on and so forth. Now, because I want to do this sort of in general, obviously in this case I could call this x3, x4, x5, but what I'd like to do is I'd actually like to call this xn minus 1 and this xn. So we're dividing it up into what are called n partitions. There's 1, 2, 3, 4, down to n partitions there. And usually we use the sort of notation that the gap in each of these, sort of the size of each partition, is delta x. So the width in between each of these is delta x here. I'm just going to indicate that they're all delta x. And we get a nice sort of relation here that delta x is equal to b minus a divided by n, right? You take your interval and you divide by how many partitions you want to do. So let's start off by talking about something like the left end approximation. So the left end approximation, what it attempts to do is it attempts to make a series of rectangular approximations to the area under the curve. Remember that the area that we're trying to estimate here is this stuff here, the area under this curve and above the x-axis. So what the left end approximation sort of does is it uses the left endpoint of each interval. So it would say, okay, let's use this one here, then build ourselves a rectangle, and we would go down to here, and that would be our first rectangle. Then we would take this point, use that left end, go across, have our second one, then our third one, then our fourth one, and in this case, our fifth one like that. And you can see that, of course, this is only going to be an approximation. Obviously, this in this case, my left end approximation is going to overestimate the area because these rectangles are too tall, but it would be an approximation of the area. And of course, the more partitions you do, the smaller those delta x's are, the better the approximation is going to be. So what does the approximation sort of look like? Well, what we're really doing here is it is equal, well, we are going to have to figure out the area of each of these rectangles. Well, the area of a rectangle is the height times the width. So in this first rectangle here, the height is at that first endpoint, so it would be f at x sub 0 times the width, which is that delta x. So we'd have times delta x, and then we would add that to the next one. The next one had height at f of x1, so f of x1 times delta x again, because again, the width for all of these are delta x. And then we would continue doing that until we got to the sort of last one. Now notice that the last one would actually be here at xn minus 1. We wouldn't use b because b would give us a rectangle since we're using the left end approximation that wouldn't be under the curve or in the interval we're interested in. So the last one we would actually use would be xn minus 1. So f of xn minus 1 times delta x. And that would be our left end approximation. Now, probably some of us know a nice cleaner formula for this. What you could do is you could factor out that delta x, and you could get that as delta x times f of x0 plus f of x1 plus dot 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 f of xn minus 1. So that's usually how we sort of formulate the left end approximation. Okay, so that is your left end approximation. Now let's try to do the same thing with the right endpoint approximation. So we are going to sort of redraw our diagram real quick. But again, we won't have to be quite as specific because we sort of know the major ideas there. So there's our sort of curve. Again, just an arbitrary curve on A to B. And again, we're cutting it up into these sort of pieces here. We're calling this one x0, x1. This one would be xn minus 1. This one would be called xn. And again, our goal is to estimate the area in here. So if we were doing a right end approximation, we would be doing the same sort of thing, except we would use the right endpoint of each thing to build our rectangles. So for this first one here, we would say, okay, let's use this, go up to there. So we'd start our height would be right there. But since it's the right end, we would actually go off over there and make our rectangle. You'll notice that the right end of the rectangle is what's defined by the curve there. Then the next one would look something like that. And then the next one would look something like that. And then the next one would look something like that. This time I drew it with only 4 partitions. But again, we're going to do this for an arbitrary amount of partitions. So what would this be equal to? Well, the first value that we used for the height was x1. So we'd have f at x1 times the width, which would be delta x, plus f of x2 delta x, plus we would go all the way down. And in this case, we actually did use the last one, which was b, or in our notation, x sub n. So we'd say f of x sub n delta x. And same sort of trick, you can factor that delta x out, and you can say, okay, that's delta x times f of x1 plus f of x2 plus dot 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 f of xn. So these are probably the first 2 approximations people learn about. They're very, very similar. The only difference is that on the left end approximation, you use the left endpoints, which end up being the start of your interval up to the second to the last, which in our notation is x sub n minus 1. Whereas with the right end approximation, you skip the beginning of your interval. You use everything else, including the end of your interval, x sub n, or in terms of letters, b. Okay, let's go ahead and look at this one slightly more complicated one. As you can notice that the sort of downside of these 2 approximations are that in a monotonic function, meaning a function that is headed in one direction, like the curve I drew for my sort of typical f of x is just like this, right? I could have drawn anything, but I drew a sort of strictly decreasing function. You'll notice that the left endpoint approximation was going to be a overestimate, and the right endpoint approximation is guaranteed to be an underestimate. So what if we sort of chose midpoints instead of always choosing the leftmost or rightmost? That's what's called the midpoint rule, or the midpoint approximation. So let's go ahead and talk about that on another page. So for this, same diagram. Okay. So again, just an arbitrary function. Doesn't matter what the function looks like, but we're just using this one. So we're cutting it up into some pieces here, like that. Same sort of notation. This would be xn minus 1. This would be xn, because again, it could be an arbitrary amount in there. And our goal is to approximate this area in here. Okay. So now we're going to do a midpoint approximation. So what we're going to do is, instead of using these endpoints of the intervals, what we're going to do is we're going to choose the midpoint inside. So we're going to choose this, and we're going to call this x1 star. And then we would call this x2 star. And then this last one here, this would be xn star. And that is the midpoint of each of those. So literally the middle of each interval. What that basically means is that xk star Well, if you think about like x1 star is between x0 and x1, so the general formula would be xk minus 1 plus x sub k divided by 2, the literal midpoint of each one. Then what we're going to do is we're going to go up to our function there. We're going to go a little bit to the right until we hit x1 and a little bit to the left until we get back to x0. So that's sort of ugly there. Don't know why that looks so weird. There we go. So there's my first rectangle. Then I'd have one here. That would be this way and this way. Then I would have one here. Go this way and this way. And then have one here, this way and this way. So in this case, the approximation that occurs for the function, the height, is going to be based on those midpoints. So what would this look like? Well, the first one would be f of x1 star. And then, of course, the width is still going to be that delta x. So times delta x plus f of x2 star delta x plus dot 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 down to this last midpoint, f of xn star delta x. And then we can factor out that delta x in a very similar sort of style and get this sort of formulation for the midpoint approximation. So we take delta x and we multiply it by the sum of the approximations of our function at each of those midpoints. Now you can hopefully see visually why even in this sort of basic case, the midpoint approximation is a better approximation than the left endpoint and right endpoint. In this case, this part here is an underestimate, but it's sort of compensated a little bit by the overestimate, then underestimate and a little bit compensated by the overestimate. And so this will be a much more accurate approximation, even when the number of partitions is the same as what we had for the left endpoint and right endpoint approximation. So this is just a quick review of sort of 3 basic approximation methods that you guys hopefully had already sort of seen from your Calc 1 class. I wanted to go back and try to draw these diagrams, but I also want to make sure that we have a nice page sort of summarizing the formula of each of these. So these sort of 3 diagrams that I just drew sort of hopefully show you guys where the formulas come from. But let's go ahead and summarize everything we just said about these 3 approximations. So this is a summary of the left endpoint, right endpoint, and midpoint approximations. So for this, we're going to assume that we have an f of x, a continuous function on some interval a to b. And we're going to suppose that we're going to choose n partitions. So we're going to chop it up into n pieces. Then the size of each partition will be given by delta x equals b minus a over n, which makes sense. And we're going to further suppose that we set up our x0, x1 in this way. x0 is equal to a, x1 is x0 plus delta x, x2 is x1 plus delta x, each x sub k is the previous one plus delta x. And then x sub n would be x sub n minus 1 plus delta x. But since x sub n is going to be the end of the interval, it'll also be equivalent to b. So we start at a, we go to b by the size of delta x. Then we have the following approximations. And you'll often see this notation, L sub n, meaning left end with n approximations, R sub n, right endpoint approximation with n partitions, and M sub n, midpoint approximation with n partitions. And these are the sort of cleanest formulas we have. For L sub n, it's delta x times f of x0 plus f of x1 plus dot 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 f of x minus 1. So you use x0, x1 all the way down to xn minus 1. If you count in here, if you count 0, 1, so that's your first one, your second one, all the way down, you'll have n evaluations here, which makes sense. If you have n partitions, you should evaluate n times. Here, we use starting from f sub x1, which is technically going to be a plus delta x, and then we go f of x2 plus dot 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 down to the very last f of xn, which will be f at b, the end of our interval. And then the midpoint rule is delta x times f of x1 star plus f of x2 star plus f of xn star, where those xk stars are the midpoint of the sort of previous partition. So x sub k minus 1 plus x sub k divided by 2. Now, interestingly enough, the midpoint approximation that we're learning is the standard one, which is literally the midpoint in the middle. But of course, you could come up with other midpoint approximations if you wanted to. You could come up with, say, the 1/3 midpoint approximation, where you divide up, instead of, if this is one end and this is the other, instead of picking the thing directly in the middle, maybe for some reason you decide to pick the thing that is 1/3 of the way. So you could come up with a different sort of approximation style. Might not be as good, might not have as much of a reason for why we'd want to do it, but this is only one of many midpoint style approximations we could do. So these are the sort of 3 basic approximations that we just discussed and sort of their summary there. In a few minutes, we will go ahead and do an example of actually, with a particular definite integral, setting up these approximations. But before we do that, I'd like to derive one more approximation that's based on a slightly different shape. So this is what I would consider the first new method of approximation, because this is not something you probably saw in your Calc 1 class, which is called the trapezoidal rule. So once again, let's get a derivation sort of going. So we're going to have our sort of same setup here. So there's our curve. We're imagining that we're going from A to B, and we're going to cut this thing up into some pieces. Again, equal size. We're going to call this x0, x1, x2, x3. We don't need to say x3. This will be x sub n minus 1. This will be x sub n. Same thing, delta x, b minus a over n. Okay. Instead of drawing rectangles, though, this time, what we're going to do is we're going to take two approximations. So I'm going to approximate here and here. And then what I'm going to do is I'm going to connect those via a straight line. And I'm going to create a sort of weird looking shape that is rectangular sort of on these three sides, but then has a sort of diagonal top. This is actually a trapezoid. Then here we would do the same thing. We would use this one and this one. Sort of draw a line there. Then we would use this one again and this one. Draw, there we go. And this one and this one, so draw. And then finally, this one and this one, which would be almost flat, it looks like, almost rectangular, and there we go. So this is a trapezoidal approximation. So instead of using straight rectangles, we're instead using trapezoidal shapes that in this case sort of look like that. So let's go ahead and think about how we determine the area of a trapezoid. So if we think about area of a trapezoid, well, we might remember from geometry that the sort of way of coming up with the area of a trapezoid is you take the base times the average of the heights. So it's height 1 plus height 2 over 2. So that's the area of a trapezoid. You take the base, and instead of multiplying by the height, but it's not rectangular, you take the two heights, the tallest height and the shortest height, and you average them together. So let's do that to come up with our trapezoidal approximation. Okay, so our first one, well, is going to have base delta x. So we're going to have delta x, and then it's going to be times, well, the height 1 would be here, which would be f at x0. So f of x0 plus f at, then the second one is going to be at x1, so f of x1 over 2. And then plus delta x, and then the next one's going to have f of x1 plus f of x2 over 2. And then plus dot 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 down to delta x. The last one, which is going to involve that, is going to have f of xn minus 1 plus f of x sub n over 2. So that's going to be our approximation. Notice these aren't base times height because they're not rectangles. They're base times the average of the heights, which is how you calculate the area of a trapezoid. Now, this is a little bit messier, but we can actually be sort of clever here and factor out. Notice that every one of these terms has a delta x and also a divide by 2. So we can factor this out as delta x divided by 2. And then notice we'd have f of x0, but then plus f of x1. But notice we're going to get another f of x1. So you're going to get plus 2f of x1 plus, then of course this f of x2, there would be an f of x2 in the next one. So you get 2f of x2 plus dot dot dot. Down here, this would be the second time you saw f of xn minus 1. So you'd have 2f of xn minus 1. And then you'd finally just have f of xn. So this is a very sort of different approximation because what you will notice is that the first and last don't have any coefficient on them, but everything else has a 2. And that's because every other approximation is going to be used twice. You can sort of see that visually because like this x sub 1, it's used as the right end of the first trapezoid, but it's also used as the left end of the second trapezoid. That's why we ultimately have a 2 of x, f of x sub 1. For x sub 0 and x sub n, those are only used once. This one is only the left end of the first trapezoid, and this one is only the right end of the last trapezoid. So that's why we have this sort of weird formula where everything in the middle gets a multiple of 2, but the two ends do not. So let's summarize this trapezoidal approximation here. So this is a summary of the trapezoidal rule. Once again, f of x is continuous on some interval a to b. We have n partitions. Again, the size of each partition, delta x, is going to be b minus a over n. And we're going to further suppose we have the same setup where x sub 0 is a, and then each one is delta x further, and ultimately having the last one be x sub n equal to b. Then the trapezoidal rule with n partitions says we should take delta x divided by 2 and multiply that with f of x sub 0 plus 2 f of x sub 1 plus dot 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 2 of f of x sub n minus 1. So everything in the middle gets a factor of 2, and then f of x sub n. So this is a new approximation formula based on a different shape. Trapezoids are still easy to find the area of, which is why we use this as our new approximation, but it is different than any of the sort of previous three because all those were based on rectangular approximations. This is based on a trapezoidal approximation. Okay, so let's go ahead then and actually take a look at applying these different approximations to an actual definite integral and just making sure we're good with setting all this up. So here's a definite integral, the integral from 1 to 3 of 1 over the square root of x cubed plus 1. This would be a very, very unpleasant integral to attempt to do. I'm not even sure if it is doable. The reason that this would be pretty unpleasant is while we have dealt with radicals, we've dealt with radicals of something squared plus 1, where we can attempt something like trigonometric substitution. This is an x cubed, which is going to make things tremendously harder. So this would be definitely something that is either very hard or possibly impossible to actually do directly. In other words, it would be almost very, very challenging to try to come up with an antiderivative and then plug in 3 and 1. So instead, what we're going to do to try to estimate this is we're going to write down and evaluate expressions for L4, R4, M4, T4 for this integral. Now, when you guys are doing this on your own, you are welcome to draw a diagram of the curve. I don't think that's really necessary, but what is absolutely necessary is I would draw a number line showing the interval you're working in and showing those partitions. So let's go ahead and draw ourselves a number line. We are working on this from 1 to 3. And we know also we can figure out our delta x for all of this, which is going to be our b minus a, 3 minus 1, divided by the number of partitions. For all estimates, we're going to be doing 4 partitions. So 3 minus 1 divided by 4, which is going to be 1/2. So let's go ahead and label this going by 1/2. So this would be 3/2 then. This would be 2. This would be 5/2, and then we'd end up with 3. So in our notation, this is x0, this is x1, this is x2, this is x3, and this is x4. Notice it makes sense. We're doing 4 partitions, and the last one is x sub 4, and the first one is always x sub 0. So I would always take the time to write that out because it'll make writing out the approximations much easier. So for L4 then, well, what do we need to do? It's going to be delta x, which is that 1/2, times the function evaluated here, 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 and here. The function is this thing right there. So it's going to be 1 over the square root of 1 cubed plus 1 plus 1 over the square root of 3/2 cubed plus 1 plus 1 over the square root of 2 cubed plus 1 plus 1 over the square root of 5/2 cubed plus 1. And there we go. Just for fun, I'll go ahead and just label for left end approximation. We are using these 4 approximating points. So using those 4 approximating points. Now, again, most of the time, to be honest, you are just going to be asked to set up a do not evaluate because we're not really interested in having to do a lot of calculator work. But if you wanted to, you could come up with an actual approximation by typing this stuff into your calculator. So you'd have 1 divided by the square root of 2. Plus 1 divided by, looks like, you get plus 1 divided by square root, what is that, 9 divided, or 27, sorry, because it's a cube, 27 divided by 8, plus 1, and then plus 1 divided by square root 8 plus 1, and then plus 1 divided by the square root of 125 divided by 8 plus 1. Okay, and then times 1/2. So it looks like when you do that approximation, I'll just keep 3 decimal points. It looks like it should come out as about 0.882. So there's our left end approximation. To be honest, most of the time you guys are just going to be interested in setting up this, but just in case we wanted to look at an approximation, there we go. All right, let's go ahead and do R4, the right endpoint approximation. That means we're going to be using these values here. So this will be all those sort of red points. It's going to be 1/2, and then we're going to have 1 over the square root 3/2 cubed plus 1, plus 1 over square root 2 cubed plus 1, plus 1 over square root 5/2 cubed plus 1, plus 1 over, it doesn't really matter, but we were writing everything else not in the actual color. Apologize, let's just try to stay consistent there. So we'll just go back and rewrite that in the normal color. So you get 1/2 and 1 over square root 3/2 cubed plus 1, plus 1 over square root 2 cubed plus 1, plus 1 over square root 5/2 cubed plus 1, plus 1 over square root, last one, which is at 3 there. So we have 3 cubed plus 1. All right, if we do that approximation, we should get something close to, but of course not the same as what we got before. So we have 1 divided by the square root of 27 divided by 8 plus 1, plus 1 divided by the square root of 8 plus 1, plus 1 divided by the square root of 125 divided by 8 plus 1, plus 1 divided by the square root of 27 plus 1, and then times 0.5. So we'll see that, we get a pretty different sort of value here, 0.6, looks like 23. So there we go. There's our right end approximation. Obviously, these are pretty different, and that's mostly because we're only doing 4 partitions, so the accuracy is not particularly high here. All right, and let's go ahead and do the midpoint. For the midpoint, we are not going to be using any of these, but we're going to have to establish the midpoints of each of these. So we will have to use these 4 midpoints. So what are those midpoints going to look like? Well, the midpoint between 1 and 3/2 would be 5 over 4, and then this would be 7 over 4, this would be 9 over 4, and this here would be 11 over 4. And of course, if you're unsure about that, you can simply average these numbers together. 1 plus 3/2 divided by 2 is going to give you that 5/4 there. So let's go ahead and write out that approximation then. So this is going to be our midpoint with 4. Okay, midpoint with 4, so that's going to be 1/2 again. And then we're going to use those midpoints, so square root 5 over 4 cubed plus 1, plus 1 over square root 7 over 4. 7 over 4 cubed plus 1, plus 1 over square root 9 over 4 cubed plus 1, plus 1 over square root 11 over 4 cubed plus 1. All right, and let's go ahead and feed that through and see what we get there. So 1 divided by the square root of 5 divided by 4 cubed plus 1, plus 1 divided by the square root of 7 divided by 4 cubed plus 1, plus 1 divided by square root of 9 divided by 4 cubed plus 1, and then plus 1 divided by square root 11 divided by 4 cubed plus 1. And if we go ahead and divide that by 2, looks like we should come out with something about 0.738. Yep, about 0.738 there. So that's our midpoint approximation. Notice that the midpoint approximation landed between the left end and right end point approximation. That isn't always guaranteed to happen, but it will happen for anything that is a monotonic function, meaning a strictly increasing or strictly decreasing function. And this is a strictly decreasing function. So that left end point approximation is guaranteed to be an overestimate, and the right end is guaranteed to be a an underestimate. So this being in the middle makes sense there. And then finally, let's go ahead and do our trapezoidal rule. So which points did the trapezoidal rule use? Well, it uses everything. I mean, not the midpoints, but it uses all the originals. So it'll use every one of these. Remember, it's going to use all the sort of middle values twice, and these ones just once. So for the trapezoidal rule, what we're going to have is we're going to have 1/2 divided by 2, delta x over 2, 1 over the square root of 1 cubed plus 1, plus 2 times 1 divided by the square root of our next point after 1 was 3/2. So 3/2 cubed plus 1, plus 2 times 1 over square root 2 cubed plus 1, plus 2 times 1 over square root 5/2 cubed plus 1. And then, of course, we reach the last one, where we will not multiply by 2 because we're on the last one, and this 3 is only going to be used once, just as the right height of the last trapezoid. So 1 over square root 3 cubed plus 1. Okay, and if we type all that stuff in, looks like we should get 1 divided by square root of 2 plus 2 times, or 2 divided by square root of 27 divided by 8 plus 1, plus 2 divided by the square root of 8 plus 1, plus 2 divided by the square root of 125 divided by 8 plus 1, plus 1 divided by the square root of 27 plus 1, and then we got to divide that by 4, because 1/2 over 2 is 4 out front, and it looks like that should come in as about 0.752. Oh, sorry about that. 0.752 there. So there we go. There's actually going through and writing out 4 approximations and actually evaluating them for what would be a very challenging definite integral. Now, I will make a quick mention here. In general, you guys are probably going to see a lot of questions that say write down and do not evaluate. So you would just be trying to write them down into this sort of form here. Or if you wanted to be really clever, you could just state the points that you were evaluating. So you could have written this as like f of 1 plus f of 3/2, and then just make a statement with f of x equal to 1 over square root x cubed plus 1. So we'll see some examples of that in our next video. So it's just how do we write this out without having to plug everything in. But I wanted to make sure we did at least one evaluation so you could actually take a look at it. The other big thing that we have to do in this section too is that while it's nice to be able to build these approximations, what is more interesting from a theoretical perspective, because obviously performing these approximations is more something suitable for computers, what's interesting from our perspective is understanding how accurate these approximations are. So in the next video, we'll begin to study what are called error-bound estimates for the midpoint and trapezoidal rules.